entitled as photon mass, conformity with the special relativity and Gauss invariance. The title was given so because according to special relativity, the photon cannot have a mass. Because Einstein's theory of relativity predicts that photon must have a non-zero mass, that means zero mass, because the equations don't work out if there is a mass. So we'll try to show why the photon mass is actually zero. It appears to be zero, and try to formulate a theory. It is actually a model by which we can show that the photon can have a mass, although it does not reveal its mass in the normal physics, realm of physics. Okay, the term photon was first given by Lewis in paper The Conservation of Photons in the Journal of Nature. And since then, photon was a subject of very great interest. During the years 1936 and 1938, a student of Louis Broglie, Alexander Procar, he modified the Maxwell's equations of electrodynamics, which are the known equations that govern the electromagnetism laws, but he modified it and tried to accommodate a non-zero photon mass, thereby allowing it to be compatible with the special theory of relativity and Gauss invariance. Although there are certain problems because Procar's equations implied velocity dispersion, which is a problem, but still the Procar equations play a significant role in superconductivity, where the photon has been found to have a mass, a very small amount of mass, but still it has been found to have a mass while it interacts with the Cooper pair. Next slide, please. It is a mission of a work to provide an explanation why the photon is like this, why its behavior is so cumbersome. I mean, why the photon does not reveal its mass, although it might have mass. Because you see, in superconductivity, since it has been observed that the photon has mass, so there must be a massive nature of the photon. Otherwise, why would it have a mass? But still, it appears to be massless in normal physics and normal physical laws of those things. And it has been found that if photon has, photon's mass is put to zero, then all the theories, the QED and the other weak interactions and all these theories remain good in good agreement with experiment, which is good. But still, we must face the truth that if it has some mass, then why doesn't it reveal it? Or if it doesn't have a mass, then why does it show a mass in superconductivity? There must be some reason behind it. So we consider some additional hidden dimensions along with the spatial dimensions which we know. Actually, we know that there are 3 spatial dimensions and 1 time-like dimension. But there might be additional hidden dimensions which come out from string theory. They are the essence of string theory. They are sometimes called in string theory compact dimensions. And this thing might explain the mass of the photon. Our method is analogous to the Kaluza-Klein method. Kaluza and Klein were scientists who tried to unify electromagnetism and gravitation using these extra dimensions. Next slide, please. We assume that the frequency is a function of the wavelength lambda. Of course, we know that the equation that frequency equals to velocity, and they are related by the velocity and lambda, and all these things are related. We assume it is a function, the frequency is a function of lambda, and we consider an extra dimension to this lambda. Extra dimension to this lambda, and we assume that it is curled up in a very small sphere, it's a very small circle of radius r, and in the periphery of 2 pi r. So we make the identification lambda equals to lambda, capital lambda plus 2 pi r. This is the capital lambda. So this identification allows us to assume that this frequency is a function of these 2 things, where a and b are constants. This is the function of the small lambda, and this is the function of capital lambda frequency. So we name this as the string frequency. This thing is a string frequency, and a and b are constants. Now after this thing, we use the Lorentz series expansion. This is an expansion of mathematical tool which allows us to expand it like this. where A is the function and N are constants and B are constants. This is the Lorentz series, and we use this series to determine the mass. It is very complicated mathematical work, which is not I cannot show it here, but we will get the result. And the result we obtain after resorting to the normal energy momentum dispersion relation of Einstein. We get ms gamma whole square equals to m0 square plus mc square, where ms gamma is the total mass of the photon, mc is the compact mass, and ms gamma is the total mass, m0 is the 0 point photon mass, which means it is the normal mass of the photon, which we can assume if it exists, although it is considered as 0. But just to adjust to our theory, existing theories, we take it as 0. But if it is not necessary that photon mass has to be 0. In fact, it has been found that a non-zero photon mass can also have very interesting implications. From this relation, we can get an interesting result that if the is that the m0 is the normal mass, we can see that m0 square equals to ms gamma square minus mc square. I mean, this is the square root, and we find that m0 equals to plus minus and the root over 3, which suggests that the photon mass can be negative also. And we'll see, this is actually a hypothesis, but still we'll see that this negative mass is the actual reason why photon mass appears to be 0, because it cancels out. We'll see later. Next slide. Okay, here we consider a cohesive field. It is just for the time being we name it mother field. It is not any physical term, just to name it. So we postulate an ubiquitous field is only present everywhere. The birth of our universe, which was there in the birth of our universe, and we make the following assumptions. Okay, so the assumptions or the criterion are: it is assumed to be comprised of infinite number of point energetic vector fields. So these fields are denoted by EI. I mean, they are point-like in nature because we know the vector emanates from a point. Therefore, we make point energy. This is just an assumption. The quanta of this field is termed as the mother photon, but it is not the same photon as we observe here in the present world, or what we observe in experiments. The energy of mother photon is given by E ms gamma whole square. Ms gamma is ms gamma we found there, the same thing, except this field is totally different. It is a hypothetical field. Next slide. Okay, next we consider transformation mapping. What is mapping? Mapping is T is a mapping from E to E, where E is the set and EI are component fields. EI all belong to E. So if E maps to E, T is such that E maps to E is termed as a transformation mapping T. The implication of this transformation mapping is seen in the next slide. Next slide. Okay, now we introduce the Brouwer's fixed point theorem. What is this fixed point theorem? It is a theorem that states that if one set of points maps to another set of points, then there is one point that remains fixed. It doesn't change after the mapping. And it was named after mathematician Brouwer. There is another fixed point theorem called the Kakutani fixed point theorem, but it is not very interesting. This one is very interesting. So this concludes that if we apply this fixed point theorem to the mapping we saw earlier, then you can see that there will be one point in the set E that is fixed. That means there must be at least one point in energetic vector field which remains unaltered after the transformation T. And this unaltered field after transformation T is one of the observed physical photon, which is the energetic field and not mass. So this we postulate that unaltered field which remains fixed after transformation T is the observed physical photon field, and it is energetic and not massive. And we state that this is the Brouwer's fixed point criterion, which means that since this is an energetic field and not a massive field, the photon doesn't reveal its mass, because since it is an energetic field, it is an hypothetical criterion, just name. And this criterion prohibits the photon to remain with mass given by energy. Okay. And using this our theory that we used, we found that m0 square equals to ms gamma square minus mc square. Putting it in the normal Einstein dispersion relation, we find that E square equals to discuss C square and this thing. This thing is kind of similar to the relation which Siddharth found. It's kind of analogous. So the terms are very different, but they might conform to each other. Okay, I mentioned this earlier that photon's mass is being found that plus minus. Generally, we can neglect the minus thing, but suppose it is not, it cannot be neglected. Suppose, because when Dirac gave his found his theory of electron, he said that the energy levels can exist in negative levels. So it is not totally unphysical. Maybe there is some negativeness. When Dirac proposed it, he found the wave functions and he saw that there were some negative energy levels, and he didn't neglect the negative thing. That's why the electron's theory was modified and it became a good explanation for what happened. Now, next slide. Space and one is the dark space in quantum mechanics. So these two are the relations that we propose. So one has the eigenvalue plus m0 and one has the eigenvalue minus m0. So we get two things here, plus m0 square and minus m0 square. So two mass square values plus minus m0 square plus minus m0 square. Again, if we take the expectation value of the operators m and m dagger, you see that one expectation value is given by plus m0 and the other expectation value is given by minus m0. So if sum is taken out of two expectation values, it becomes 0, which justifies and suggests that the photon mass is 0. Because since the two expectation values are 0, the sum of the two expectation values are 0, so there can be no total mass of the photon, which is 0. This is the rationale for these operators which are here. So this is the combination states of the one states. This is just combination states. Since we got two values, plus m square, plus m0 square, minus m0 square, they can be achieved in three ways, actually 4 ways. Plus m0 and plus m0 give plus m0, minus m0 minus m0 give plus m0, and these two give the same thing, plus minus, this is minus m0. So we have plus m0 square and minus m0 square. Now these two things, the plus m0 square state and minus m0 square state, these two things are important since they will be shown in the next thing. They agree to that is the energy of the photon, which is given by E equals to Pc. But the normal Einstein's relation is by E equals to P square C square M0 square C4. So it is normally put because of this relation. Since the photon's energy is given by E equals to Pc, we think that M0 must be 0. That's why we get E equals to Pc. It is normally taken so. But if we have the mass square values, then we have these two equations. We can divide it into two component-like equations. One is given by E1 square, this one and this one. So these two relations, this one and this one, if they combine, they will give E equals to Pc. One corresponds to the plus m0 square value and the other corresponds to the minus m0 square value. So if we take into consideration the mass square values, two different mass square values, it is not necessary to assume that the photon's mass is 0, which has been done for so long to adjust the theories mainly, just like it was done in the Greek years when they did to explain the model of the universe and all these things. They use epicycle theories, and here it has been always used that the photon's mass is 0 because this thing doesn't satisfy and this thing doesn't satisfy. But if we use this mass square values, it is not necessary to assume that. So we get the general formula of energy of the photon if we use two mass square values. So it's not necessary entirely to assume that the photon's mass is 0. I mean, it may show to be 0. It may show to be 0 in other things and other many places, but it is not necessary that it has to be 0. Because we saw that the photon exists in two states, plus m0 minus m0. So even if the photon has a mass, because of these two states, the sum will give of 0 photon mass, and the photon mass appears to be 0. Although it might not be 0 if we can separate the two components, but I don't know if it is possible. Maybe in high energy experiments it will be possible. Okay, by the methodology we did in the previous section, we found E equals to MC, E equals to PC, sorry, the energy of the photon. The same can be observed in case of electrodynamical equations and the velocity dispersion law. Now this velocity dispersion law is observed for photon that it is given by k plus c square equals to omega square. But in Foucault's equation, it was found that there was a dispersion, there was a variation from this law. That's why it is not very famous. But if you use that law, so that's why a mass term is never added in the Lagrange. Can have a mass. Minus especially.
So it's already there, the notion was already there.
Notion is already there, but it is not been theoretically based quite properly because we don't have.
Please show me previous. What's this one? What you have this attention, and you speak that everything okay with this Lagrange. What is cumulative? It is current.
Yes, ma'am, the current.
Current.
Yes, ma'am.
But what is current structure? Because if you have massive photons and you have 10 under square.
I mean,
How it
there is
goes?
m0 square and you predicate it gets cancelled because plus m0 square minus m0 square. I mean, there
It
is
is not here.
no. I just given the direct result here. I told this paper is not full paper. I have given the direct result. The calculations are not here.
Gmail has no underlying thing, and
This is not, if the geometry is 0, then we don't need this geometry. Which one are you saying?
I want to tell you that
Yes, ma'am. That is because we take an m0 square term and m square, not geometry. m0 square and m square. And because of the m0 square, this term is just geometry mu.
yes,
And there is another.
equation Russian must have a
considered the photon to be massless in the U1 and U1 range. But here we are saying it has a mass, but it is very small. And
Smaller, for field, quantum field theory, it is nothing. If you have the mass.
This is powerful, like when you are
no, look at it this way. The mass of the photon square
this one is square.
can be neglected.
Oh, negative. It is.
Neglected.
It is. Neglected, it is approximation.
Yes.
Yes, then if it is M0 equals to 10 to the minus
But I
16.
speak about it. No, dispersion, I understand. Dispersion, yes, okay. If it runs with some data or something,
But now Schwinger has shown that, Schwinger showed that it goes in ways not
yes,
makes
I know Schwinger.
is what
Schwinger has-
Maybe we
The
can
vector
discuss
system.
this later. We can discuss this one later.
Later. I told him that I shall discuss it.
You can take the paper and read it.
Yes.